Hi, this project is about some experiments that we did training models that have been used for music representation learning with very limited data, so with subsets of a data set that are extremely small, and seeing what happens. And we think some interesting things came out. I'm Christos, I'm a PhD student at Queen Mary at the Center for Digital Music. I did this work with Emmanuel Benetos, who is a reader, and Johan Pavels, who is a lecturer at Queen Mary. Representation learning has been widely adopted in music research and in the field of MIR, music information retrieval. It used to be that people would design and use handcrafted features and often pair them with a small classifier. That sort of shifted towards trying to do this more end-to-end, so starting from the waveform or spectrogram, more raw data representations, and having larger classifiers. But lately it's been very successful to use all kinds of pre-trained models. There's some in music based in mass modeling, autoencoding, contrastive learning, extracting features, and then using a small classifier. And that has been shown to increase performance in many MIR tasks. Now, we all know that massive models perform better with more data, approximately. But what's the case for more humble-sized representation learning models that are currently used in music that also are under the constraints of generally more limited or smaller data sets because of copyright concerns in music? There hasn't really been a systematic evaluation of how much data matters in smaller scales and slightly smaller models. This could be useful for in-domain representation learning. Right now, it's not clearly demonstrated that large models pre-trained on Western music, for example, can transfer to music of different tuning systems, especially when there's limited data. For the medium-sized representation learning models used in music, we also don't know how their architecture and pre-training paradigms affect how well they scale with data. And we're also not sure how much the representation itself impacts the overall performance. Obviously, in representation learning, you have sort of two main stages, the pre-training and then the fine-tuning, usually frozen fine-tuning. Is the representation critical to performing well on the downstream task? This includes questions of how far we've come in comparison with handcrafted features, and what kind of performance different models downstream might be able to recover from a, quote, bad representation. There's actually been some work training general audio classifiers, so not representation learning, with limited data, different kinds of classifiers showing consistent improvements with more data. There's also been some work showing that even randomly initialized CNNs, especially those with carefully designed filters, can actually perform decently in audio classification, showing the impact of the architecture itself. But that still doesn't cover the interesting case of representation learning, where you have a whole other model that can recover potentially performance from a bad representation. And there hasn't been a systematic evaluation of different architectures, paradigms, and different tasks. So in summary, what we decided to do is take a few music audio representation learning models and pre-train them on very limited data, and then take these models, freeze them, and use the features for different downstream tasks and see how they perform. We selected a few different models with different architectures and pre-training paradigms. All of these have been used in music before for representation learning. VGG is a sort of small version for music of the original proposed VGG network. Musician uses more carefully designed filters to tailor to the music domain. And we also selected the audio spectrum transformer. All of these are trained in a supervised fashion on tagging. We also selected CLMR, which is a music version of SimClear, trained in a self-supervised manner with various augmentations, and AudioMay, or a transformer masked autoencoder, a relatively small in size version. For pre-training, we choose to use the Magna-Tagatune dataset. It's one of the most popular datasets in MIR. It contains around 25,000 tracks, 30 seconds each, and it's a music tagging dataset, usually used with just the 50 most common tags in the dataset. It's multi-label and weakly annotated. We then create a subset of this dataset with tracks that belong to at least one of the top 10 genres in the dataset. And we create different subsets with different amounts of data. So for example, for n equals 1, we choose one track from each of the 10 genres. So n equals 1 will be a subset of 10 tracks, each belonging to different genres. For n equals 2, we would have 2 tracks from each genre. This results in subsets from 5 to 500 minutes. The reason we choose the system is because if we randomly sampled tracks, the data diversity between the subsets would be inconsistent. Therefore, we chose the top 10 genres as an indicator of a relatively fixed and representative data diversity given the limited size. We also considered 2 other cases. We denote n equals 0, the case where the model is actually not pre-trained, so just randomly initialized without any pre-training, and the case of using the whole training subset of the dataset, which is about 8,000 minutes. We had to take a few other major decisions. We're sticking to the original pre-training methods from the original papers and use Adam. The reason we do this is that there are many different configurations, including regularization, for example, that would result to very different pre-training, but we want to use the models as they're generally used, so unchanged and used with different data. As our main goal is to see what would happen if we use the models in different data, rather than finding the most effective way to pre-train on limited data. Following previous work, we also don't use a validation set. Some of the reasons are that we simply don't have enough data to afford one. There's also a misalignment of source and target objectives in most pre-training task and target task combinations. So overfitting in the source task is not a direct indication of how the representation would perform in downstream tasks. But also finally, we know that these models are going to overfit, and we want to test how much performance we can recover from a quote-unquote bad representation. The downstream tasks that we decided to use are music tagging, again on the Magna Tagatune dataset. Remember that for most cases we use a very limited subset, so while there is some overlap, the generalization of the representation does get challenged in many situations. We also use TinySol for instrument recognition. It's a dataset of 14 instruments with single-stroke monophonic audio. It should be a relatively easy task for the models to solve. And finally, key detection on Beatport EDM, which contains key annotations, so for the 12 pitch classes and major or minor. There are some other details that are covered in more detail in the paper and the online repository, but we wanted to test how different downstream models would affect how much performance is recoverable from the representations. So we use a 2-hidden unit MLP and an SLP. We also compare the models to handcrafted features that have been widely used in MIR, so MFCCs, mel frequency cepstral coefficients are generally used as descriptors of timbre or the quality of sounds, and chroma is used to represent the salience of different pitch classes in the audio. Finally, we also decided to test the robustness of the models under different circumstances. So we use additive Gaussian white noise at different intervals. So 15 decibels SNR would be a relatively easy case for a human to deal with. 0 dB SNR is definitely more challenging. You wouldn't listen to radio if it was that noisy, but a human would still be able to solve these tasks even under this much noise. And finally, a very simple case of reducing the gain. The augmented audio is only used for evaluation, so not for training of the downstream models. So these are the results of the models with an MLP in the clean audio case for the different tasks. The x-axis represents the different subsets with increasing amount of data, and the y-axis represents the respective performance metric. So for Magna Tagatune, we already see some interesting trends. For n equals 1, so just 10 tracks, most representations are performing decently, apart from CLMR. We see approximately just a 2% difference between AUC ROC for n equals 1 and n equals 100, and then it's another 2% compared to the total data set. Interestingly, while most models have an upwards trend, apart from maybe a small dip in the n equals 1, 2, and 5 range, where there might be some severe overfitting, AST is decreasing in performance. This is very in line with the existing observations about AST and transformers needing a large amount of data in order to perform well. That said, the TMA model is performing a lot better than AST, which is maybe attributable to its smaller size. Perhaps the most interesting part of this is that for n equals 0, so just randomly initialized models, we see pretty decent performance for the two CNN tagging models of an AUC ROC of 86. We already saw in previous work on random audio classifiers that there could be some decent performance from randomly initialized models, but this is even more dramatic, perhaps owing to the representation learning setup. This performance of random models kind of resembles principles from reservoir computing, in which a signal is mapped into a high-dimensional space and a system is basically trained to map it to a desired output. Since the source and target task for these supervised models is the same, we can also see how freezing most of the model and just training a small probe at the end of it is sufficient to get a good amount of performance. We see similar trends for TinySol, with most models increasing performance with more data. The performance of random models is not. However, it's also evident that a handcrafted feature, MFCCs, and their first and second derivatives are performing better than all of the models on a relatively simple dataset and task, which really questions how universally applicable these models are. This is also the case for Beatport, with even more drastic performance differences between the models and the chroma features. We also don't really observe performance differences when the data increases, apart from TMA, which could mean that the models are not encoding pitch information in an accessible manner, at least, which could be an artifact of their pre-training objectives. However, some very interesting results were observed when comparing the differences between the MLP and the SLP downstream model. Here you could see how the randomly initialized VGG has very bad performance without pre-training when an SLP is used downstream, but in the same case, an MLP is able to recover enough performance for the downstream task. That also looks to be the case for Musician, which, when it overfits for n equals 2, the MLP is still able to recover performance when the SLP isn't. This means that there could be meaningful differences in how the model encodes and structures its latent space when different amounts of data are used. This difference is less pronounced for these models when more data is used, which could mean that more data is making the model encode relevant information in a more disentangled manner. However, this isn't necessarily the case for the rest of the models, which show much smaller differences between the SLP and the MLP, both for Magna-Tagatune and TinySol, Beatport as well, but the performance is bad in all cases. We also find some interesting results when the audio is augmented. In each case, the gray line indicates the best performance in the clean scenario. When the white noise is relatively quiet, we see a relatively small performance difference for different models, though models such as Musician are performing significantly worse. That's not the case for CLMR, which keeps decent performance, probably because white noise was used as an augmentation for the model to be invariant to. However, with a white noise of 0 dB SNR, all models perform very badly. Thankfully, with just a gain decrease, the performance difference isn't large. In all cases, it does seem that more data generally leads to slightly more robust representations. These experiments show that even bad representations, so ones from random models, are not necessarily bad and were performing quite well. In the Magna-Tagatune case, it seemed like the difference between pre-training data wasn't that massive. There is definitely more to investigate, though, in how entangled relevant information is at different data scales, but also for different models, as the performance of the MLP versus the SLP was different in many cases. We did also show that learned models are not necessarily a universal solution yet, and they still underperform handcrafted features in certain MIR tasks. We also saw mixed results for different models under the robustness checks, and we think that there's more to investigate in this axis in our quest to build more robust models that are suitable for real-life deployment. We hope that these results provide a reflection on our progress so far in representation learning for music and provide some ideas about how to make models to accommodate limited data scenarios and, in general, to make better music models. Thank you for listening, and feel free to email me for any questions.